Welcome to today's Explainer. We are stepping straight into the future of medicine through the 2026 framework of Lázaro López Paz. We're going to deliberately unpack the white paper on quantum sensors, biosensors, and quantum simulation for medicine and neuroscience. Now, this is highly technical territory, so we are going to take our time to parse the exact mathematics, logarithmic functions, and mechanical equations that make all of this possible.
Okay, let's dive into this. We're using a zoom-out structure for this analysis. We'll be scaling all the way from subatomic equations in quantum physics foundations up to OPMs, organ on a chip, quantum drug simulation, and finally reaching the macroscopic level with clinical AI integration.
Section 1. Quantum Physics Foundations. This is where we lay the subatomic bedrock that actually makes this technology a reality.
Let's start with the foundational math behind nitrogen vacancy centers. The governing principle here is the Zeeman effect. The formula, delta E equals G times mu sub B times B, describes exactly how energy levels separate depending on an external magnetic field. And this is what establishes our resonance frequency, F equals delta E over H. Simply put, the external magnetic field dictates the energy gap, acting as the ultimate subatomic translator in this Hamiltonian model.
To put that translation into perspective, the specific gyromagnetic factor for these NV centers is exactly 2.8 times 10 to the 10th hertz per Tesla. It's a massive constant. And it's exactly what allows us to take extraordinarily faint magnetic fields, like the whisper of a firing human neuron or the human myocardium, and translate them into highly measurable optical frequencies.
That brings us to the sensitivity equation. Eta represents the standard deviation of magnetic field measurements over time, specifically sigma b over the square root of t. Why does this matter so much? Because this precise logarithmic metric allows us to rigorously evaluate successive improvements in both NV and hexagonal boron nitride quantum sensors as the technology matures. Moving up the scale, we reach Section 2, OPMs and neuromagnetism. This is where we focus on early detection. Let's walk through OPM polarization dynamics step by step. First, dynamic polarization dP over dt balances the optical pumping rate against the magnetic field's depolarization. Second, this dynamic translates directly into measurable light intensity over time. Finally, we linearize this around an operating point. The main takeaway here is that a microscopic change in a magnetic field causes a direct, perfectly measurable flicker in light.
Now, what's really interesting about these mathematical models is how we handle arrays of these OPM sensors when placed over a human scalp. We map neuromagnetic fields into very precise data structures. We start with a data matrix mapping specific channels and times, extract the channel mean, and calculate the covariance matrix. This rigorous math acts as a topological map,